Hi, in this video, I'm going to talk about the autonomous equation and population dynamics, okay? So what do you mean by autonomous ODE? Autonomous ordinary differential equation, what do you mean by that? That's the first thing that I'm going to discuss. So as we mentioned earlier, if the right hand side of if there is derivative on the left hand side, only the first derivative on the left hand side, and if the right hand side depends only on y, there is no explicit t, then this type of ODE, ordinary differential equation, is called autonomous ODE, okay? So autonomous ODE are very popular when we model the population dynamics, meaning the growth and decline or any change of population, okay? The very first example on the population model using the autonomous ODE is exponential growth model. So what do you mean by exponential growth model is the model that says that dy over dt equals to r times y, okay? R is a constant growth rate here. R is a positive constant growth rate, because if R is positive, it will grow. If R is negative, it will decay, okay? And y at 0 is equals to y0, okay? Y at 0 is equals to y0. So this is called the exponential growth model. So if you try to solve this equation, how that look like? So it will look like 1 over y dy over dt equals to r, right? And if you integrate on both sides, you will get natural log of y. You can write 1 over y dy equals to r times dt. You can write that way too. So equals to rt plus c constant, right? Now if you want to get rid of the natural log, you will get y of t equals to e to the rt plus c, and then this can be written as, let's write down this as c1 so that it will be easy to write down. So what do you get here? If you distribute this e, so if you write like e to the rt times e to the c1, so e to the c1, let's say that is c times e to the rt. So this is basically the population growth model. But if you use the initial condition, what do you get? If you use the initial condition y at 0 equals to y0, then you will get y0 equals to c, right? Hence you get, what do you get? The final version of the solution is yt equals to y0 times e to the rt. That's what you get. So this is the solution, okay? Now what happens here is, if r is greater than 0, then for any positive initial value, for any positive population, this solution will keep growing and growing and growing. When t tends to infinity, this will go to infinity. And when r is less than 0, so when r, the growth rate is less than 0, then it will be e to the negative negative number times t, right? When t tends to infinity, this guy will go to 0. So in that case, if r is positive, then, and as t tends to infinity, you can write for r positive, right, y goes to positive infinity as t tends to infinity, right? But when r is less than 0, in this case y goes to 0 as t tends to infinity. This is the behavior of the solution as t goes to infinity, okay? So one of the disadvantages of this model is, so population cannot grow infinitely it cannot grow all the time. So it cannot grow to infinity, right? Because there will be certain constraints there, meaning that the resources, the food for example, is is finite, it is fixed, right? So it can be enough only for a certain number of people or certain number of population. So what I mean here is, the population cannot grow infinitely, okay? So there are several things that stop the population growth or slow down the population growth, okay? So this exponential growth model says that the population growth infinitely, which is not practical. So there is another growth model that depends on the carrying capacity, meaning the capacity that the certain location or certain region can has food enough to certain number of people. Okay, so that is the carrying capacity. All right. So you wrote that under the ideal condition, exponential growth model is reasonably accurate for many population, at least for a limited period of time. So the population grows exponentially for a certain number of time, for certain time only, but it does not grow like infinitely. That's what it means. Okay, but it cannot be true for infinitely long time because of the limitation on space, food supply, and many other conditions that hinder the uninhibited growth. Okay, so the next model we consider that takes into account of the resources, the limitation of the resources, is the logistic growth model. Okay, so how does it look like? That looks like dy over dt equals to r times y times 1 minus y over k. Okay, r is the growth rate, which is positive. Now look at this. So k is the carrying capacity. Okay, so k is the carrying capacity. So what happens here is, let us see that if y is less than k, so k is the carrying capacity, which is defined as the maximum number of people that have enough food into or maximum number of organisms that have enough food and location and everything to grow. Okay, so if there are too little space or too little food, and there are then the population, uh, then they do not have enough food to eat, they do not have enough space to live, right? So in that case they get they fight each other, or they get certain disease and that kill many population. So that's what happens. So meaning that if there are more people than the place or than the available food, then the growth will slow down, right? And the growth will basically, that will turn out to decay. Why is that? Look at this one. So k is the maximum number of people that can survive into that location with that given resources, right? So if y is the population, if the population is greater than the k, meaning if there are more population than the enough resources, then this fraction will be greater than 1. So 1 minus greater than 1 will be negative, right? So r is positive, y is positive, but this you will get negative number, meaning that the rate of change will be negative, derivative will be negative, meaning the population will decay, right? But if y is too small, then k, meaning that if there are too little people than the resources, in that case this y over k will be less than 1, because y is smaller than k. This fraction will be less than 1. 1 minus less than 1 quantity will be positive. At that time dy over dt will be r times y, that is a positive derivative, meaning the population will grow, so the y will grow at that time because the derivative will be positive. Okay guys, so that's what the explanation of this model. Now what we want to do is, I want to show you the solution of this the explicit solution, meaning we want to find out the exact solution by using the techniques to solve whatever techniques we learn, and also I will show you the qualitative behavior of the solution. So first of all, let us talk about the qualitative behavior of the solution. Okay, so for the qualitative behavior, what we do is we need to find out the equilibrium points there, right? You can do the qualitative behavior here, but it is easy to see from the given solution here. Okay, so it is easy to solve the equation too. So to do the qualitative behavior of the solution, what we do is we find out the equilibrium points first, and then look at the stability of the equilibrium point, right? So if you wanted to see the equilibrium point and the stability of the equilibrium point on this case, so what will be the equilibrium point? For the equilibrium point, you set this equals to 0, right? The derivative equals 0, you get y equals to 0. So equilibrium point is y equals to 0, right? Now to check the stability of equilibrium point, there are many ways. The one way is just the linearized form, meaning the right hand side will be f. Find out f prime with respect to y, right? F prime of y is just r, which is positive, right? If r is positive, then what do you get? At y equals to 0, f prime at 0 is equals to also r, right? Because this is not depending on y, which is positive. So if the derivative at the equilibrium point is positive, then the this equilibrium point is unstable. Okay, you see that y equals to 0 is unstable. If you start population close to 0 but positive, then the population goes to infinity. It blows up, right? So it is not going to y equals to 0. It is going to infinity, meaning that y equals to 0 is unstable. That's what you will see, right? It will be unstable here. Now, similar techniques will be used to find out the equilibrium points and then stability. Okay, so let us do that. So what is f of y here? F of y is the right hand side, ry 1 minus y over k, right? So what are the equilibrium points? Equilibrium points are the solution. You set the dy over dt equals to 0 and find out what you get. Y equals to 0. If you set that equals to 0, and if you set that equals 0, you will get y equals to k. So there are two equilibrium points, y equals to 0 and y equals to k. So what I'm going to do next for the, do you remember how do we do the qualitative behavior? Is we plotted fy versus y, right? Let us plot that. So if you plot f of y is the derivative term, and then y, so y equals to 0 and k are the equilibrium points. Y equals 0 and y equals to k are the equilibrium point, right? So this is 0, that is k. So this is f of y. F of y is basically the dy over dt, right? So if f of y is positive, then the function will increase. If f of y is negative, then the function y will decrease. Okay, let's look at this. If you expand this, what do you get? You get ry minus ry square over k, which is, this is a quadratic in y, right? Where the leading coefficient is negative. You see that? Leading coefficient is negative means the graph of the function f of y will be a parabola. This is a quadratic, so parabola with negative leading coefficient means which is opening downward. Okay, now you see that when you said f of y equals to 0 or dy over dt equals to 0, what we got? We got y equals 0 and k. That is basically the intercepts there, right? So that is the intercept, and we see that it is basically opening down parabola, right? You see that? You can expect the graph like this. Why is that? Because f of y is a quadratic with negative leading coefficient. Also, when you set f of y equals to 0, it is like finding a y-intercept, right? When you set that equals to 0, we get y equals 0 and y equals to, that is the basically the y-intercept here. Okay, when you set f of y equals to 0. Now, so how do I find out the highest point there? So this is a parabola. Do you remember what is the formula to find out the vertex of a parabola? We denote h and k. H is negative b over twice a. What is b? B is r here, so negative r over a is 2 times a is negative r over k, right? What do you get? So 2 twice a, right? So what do you get there? You got r and r cancel out, so you get positive k over 2. That's what you get for h. How about k? You need to plug in h equals to or y equals to k over 2 here. What do you get? R times k over 2 minus r times k square over 4 over k. So k and one of the k will cancel out. So r over k over 2, right? So rk over 2, right? Rk over 2 minus r k over 4, right? So what do you get? You will get basically rk over 4. So rk over 2 minus rk over 4 will be rk over 4. That's what you get. So this point is basically k over 2, right? So k over 2 and then rk over 4. That is the maximum value of f of y, or maximum value of the derivative. Now, to check whether it is stable or unstable, what we do here is, let us do that. Look at this. Left of 0, f of y is negative. So f of y is negative means this function is negative, means derivative is negative, because the right hand side is f of y, right? Derivative negative means the function y decreases. The function y decreases means it go that way. Okay, now between 0 and k, f of y is positive because it is above above this axis, right? F of y is positive means derivative is positive means y will be increasing. So for the increasing y, we write like this. See, you see that this point is unstable. 0 is unstable. You see that because they are going away. Now, at this point, it is going in. How about if you pick a value that is bigger than k, bigger than k? Let's say if you take bigger than k, then the graph of f of y is below. That means f of y is negative. So f of y negative means dy over dt is negative value. Dy over dt negative means y will be decreasing. So it will go like this. Okay. So it looks like 0 is unstable, right? Unstable. And then k is stable. So if you want to draw, so you can say y star. For this equilibrium, we denote by star. Y equals 0 is unstable, right? And then y star equals to k is stable. It is stable. Okay. Now, so I want to draw the solution. I want to guess the solution. The solution will look like this, right? So you see that. Let us say t. Okay. Y. So let's say this is t equals to 0. Okay. Let me use different color there. So t equals to 0 and t equals to k there. So what we just did, let me draw a dotted line for t equals to k and draw a dotted line for y equals to k, y equals to k, and y equals to 0. Okay. Now what does it say is if you start anything below 0, it will go away. So it will go away. So since y is the population, let us say that y is greater than 0 or beginning population is greater than 0 or equals to 0. So what you can see is if you start at 0, it will stay there. Okay. If you start anything between 0 and k, it will go up. You see that? Start between 0 and k, it will go to that k. So if you start here, it will go like this. Okay. Okay, the direction field will look like this. You can think. Okay, now if you start anything bigger than k, that means if your initial value is bigger than k, then it will go down. Like you see that. So you see that it is going to k. So this is go down. So what you can see from here is, see this y star equals to k is stable. Right? This is one way. This is phase diagram way. So there is another way, right? Do you remember the linearized form of checking the stability of the equilibrium point? So what are the equilibrium points? Y star equals to 0 and k are the equilibrium point. So to test the stability, what we do is you find out f prime of y. That is the linearized theorem says that, right? What is the f prime of y? Just find out the derivative of this. R minus 2ry over k, right? So at y equals to 0, what do you get? F prime at 0 will be r minus 0, that is r positive, so unstable. You see that? And if at y equals to k or y star equals to k, you can write y star. Okay, you get f prime of k equals to r minus 2rk over k. So k and k cancel out, so r minus 2r, right? So that is basically negative r, which is less than 0. So f prime or the derivative of the right hand side function at the critical point or the stationary point or the equilibrium point is negative, meaning that equilibrium point y star equals to k is stable. You see that? This is the stable equilibrium point. Okay, guys. So so let us write the so this is the qualitative way of analyzing the solution of the logistic equation, right? So what I'm going to do next is I want to show you how do I find out the exact solution, how do I find out the real explicit solution of the of that differential equation or the logistic equation. That is the next thing I want to do. Okay, so first of all, let me write down what is the differential equation is dy over dt equals to r, okay, and then y, and then 1 minus y over k, and then let's say y at 0 is equals to y0. So how do I solve this equation? By the techniques that you learned before. This is kind of in a separable form, meaning that there are this y and 1 minus y over k. You can move that side and dt on that side. So you can write like this: 1 over y times 1 minus y over k, right? and then dy is equals to r times dt, right? This is what you do. Okay, now I want to break this, I want to split this because this is in the product form, right? So I want to use the partial fraction to split this. So how do I do the partial fraction is, so you can do a over y plus b over 1 minus y over k, and then equals to, and then you solve that. But if you do the partial fraction, this is what you get. Okay, so using partial fraction, we get d1 over y plus 1 over k over 1 minus y over k dy equals to r times dt. You see that? Because if you combine these two, you will get 1 minus y over k here, and then plus, okay, plus 1 over k there, right? So what? So let me correct that. 1 minus y over k here, and then here will be y over k, so plus y over k, so negative y over k and positive y. So if you combine this, you will exactly get this. Now what I want to do is I want to integrate on both sides. Let us integrate on both sides. So integrate on this, integrate on this, and then integrate on this. Okay, if you integrate, you will get this natural log of y, absolute value of y, because this is natural log, right? Natural log takes always y, but since y is positive, you don't have to take, because we are talking about the population, right? Y is the population here, so we are assuming y is always positive. All right, so so at y equals to 0, it does not, so y is not equals to 0 also, we are assuming that, because if y is 0, then this will not be defined. Okay, now so this will be, what is the integral of this? Is the derivative of the bottom is on the top? Almost, because the derivative of the bottom with respect to y will be negative 1 over k, but there is positive 1 over k. So what we can write is negative and then natural log of 1 minus y over k, right? So let me write down that equals to rt plus c. Okay, now let us combine these two. You can write ln y over 1 minus y over k, because how do you combine two logs? Log x minus log y is log x over y, right? Equals to rt plus c. Okay, since y is positive, so what we do is, I don't want to take this this absolute value sign there, so you can write y over 1 minus y over k equals to, I'm just, because this is log means, ln means log with base e, so if you want to get rid of the log, you need to write the e to the right hand side. Okay, that's what you do. So you get e to the rt plus c, let's say c1. Okay, now if you simplify this, what do you get? You get y over 1 minus y over k is equals to c times e to the rt. Now what I'm going to do is, I'm going to use the initial value, the initial condition there. So what is the initial condition? Y at 0 equals to y0. Okay, so we will use this, but what we will do is, if y0 equals to 0, what will happen? Then in that case, so in that case c will be 0, right? Because this will be y at 0 is so y at 0 will be 0, right? Y at 0 is y, if y at 0 is y0 equals to 0, then in this case you will get c equals 0. Then you will get, this will be 0 over 1 minus 0 over k, right? So it will be e to the r times 0. So you will get c equals 0. C equals to 0. When c is 0, then you will get y equals to non-zero times 0, right? So that will be, then this implies y of t equals to 0. Okay, so if the initial condition is 0, then the solution will be 0 elsewhere. That's what we got from the graph too, right? So if y0 is greater than 0, since this is the population, we are taking greater than 0 or 0 at the beginning. Okay, if the initial population is 0, then the population will be 0 forever. If initial population is greater than 0, then what will happen is, you can write this solution as, you can write, then from here, let us write this for, we will find out the value of c later. Okay, but first of all, I want to simplify this in a simpler form. Okay, then let me find out the c first. Then c equals to y0 over 1 minus y over k. Okay, that's what you get. And y over 1 minus y over k equals to c times e to the rt implies what I'm trying to do here is I'm trying to solve for y, because since y is not 0, since y is positive, I can take the reciprocal. What I'm going to do here is 1 minus y over k divided by y is equals to 1 over c e to the rt. You see that? What I'm doing is I'm just swiping the top and bottom. Okay, swipe the top and bottom. Now, because I want to solve for y, there are two y's. I want to write only for y. There are many ways you can do this. So what I'm going to do here is 1 over y minus 1 over k. You see that? Equals to 1 over c times e to the rt. Okay, so what do you get? So 1 over y equals to 1 over k plus 1 over c times e to the rt. Now combine those two on the right side. 1 over y equals to k times c e to the rt. Okay, and then c e to the rt plus k. That's what you get. You see that? Now let's take the reciprocal. You will get, therefore yt equals to k times c times e to the rt divided by c e to the rt. Okay, and then plus k. That's what you get. Just again take the reciprocal of that. Okay guys, so what I'm going to do next is I'm dividing the top and the bottom by c e to the rt. If I do that, what will happen? Divide the top and bottom by c e to the rt, and then c e to the rt, and then c e to the rt. You see that? So if you do this, what do you get? So c e to the rt and c e to the rt will cancel out. Only on the top there will be just k. Okay, on the bottom this will be just 1, and that will be k over c times e to the negative rt. Let me write down that. Okay, so this will become y of t is equals to k over 1 plus k over c e to the negative rt. I'm moving this c e to the rt to the top, e to the negative rt. Okay, so what I'm going to do next is I'm just plugging in the value of c. Okay, so what do you get? You get k over 1 plus k times, what is 1 over c? C is y0 over 1 minus y0 over k, right? So what will be 1 over c will be reciprocal of that. That will be, so 1 over c will be 1 minus y0 over k, right? Divided by y0 times e to the negative rt. So what do you get? Let me do this. So I want to, because there is 1 in the denominator, okay, I want to take this, make the same common denominator in the denominator there. So what you do is k over y0 plus k minus y0, I'm just distributing that, times e to the negative rt, okay, divide by y0. You see that? So what do you get there then? So it will be k times y0, because it is like a fraction divided by another fraction, will be the first fraction times the reciprocal of the second fraction. So y0 divided by that. So this is what you get, y0 plus k minus y0 times e to the negative rt. So this is the value of y of t. This is the final solution, the explicit solution for the logistic equation. This is what you get. Okay, now, so what happens if t tends to infinity? When t tends to infinity, if r is positive, okay, I'm assuming r is positive there. If r is positive, then t tends to infinity will give you e to the negative infinity. That will be 0. So k minus y0 times 0 will be 0, and y0 and y0 will cancel out. So when t tends to infinity, then y of t will go to k. What does that mean? That means in the logistic equation, in the long run, the population will go to the carrying capacity. Okay, you see that we saw that actually, because y equals to k was the stable equilibrium, right? So we saw that. Now we want to do that stability thing by using the linearization form or the linearized form. So what is our f? This is f, right? This is f actually. So I think we did that already in the qualitative behavior. We did that already. We find out the first derivative, okay, of f. So what we got there? So we got we had. Let me use that. Let me do it again. So what is f of y? F of y is ry minus ry squared over k, right? We got ry minus ry squared over k. So what is the f prime of y? The derivative of the right hand side will be r minus 2ry over k, right? Let's say y is less than k over 2, okay? If y is less than k over 2, what happens? If y is less than k over 2, then what happens this? So this will be less than k over 2, right? So this will be, so y over k. So y over k is less than 1/2, right? So that means that is y over k is less than 1/2. So if it is less than 1/2, what happens to the f prime? Then f prime of y, which is same as y double prime, right? Which is same as y double prime. If f prime of y is same as this, because this is fy. When you find out the derivative of this, that is same as another derivative of this one, right? So y double prime, which is f prime of y, in that case, this will be, this quantity will be less than r, right? Because why? Because if y over k is less than 1/2, then 2r times 1 over k, 2r times y over k is less than 2r times 1/2, right? That 2 and 2. So this will be less than r. This quantity will be less than r. That is f prime of y will be positive. So when it is positive, then the curve will, the y curve, then y is concave up, right? Then y is concave up. Similarly, for y less than greater than k half, if k over 2 is less than y is less than k, then if you do that, you will get y double prime, which is f prime of y is less than 0, which is concave down. So basically what it is saying here is, so you see that what we did there was, this was t and this was y equals to k, right? So there is k half, right? There is k half. Let me use different color. There is k over 2. If your initial value, if you start from below that, it will be concave up. So it will be like, you see that? Concave up. But if you start between k and then k half, then it will be concave down. Look at this. This is what it is saying.